So today we're going to see about optimizing the networks and in two different senses. So I'm going to talk a bit about the optimizers, which are the algorithms that take the gradient information and then change the parameters in the network. And also in optimizing different aspects of training, for example, the learning rate, the initialization of the network and so on, so that we get better results and faster training, and optimizing the performance of the network. Basically, this problem of overfitting, how we can select the best networks, and how we can use regularization to reduce overfitting. And I'm going to give a brief review of the variance trade-off that we saw last semester. So let's start with the optimization algorithms that are going to find the best set of parameters for the problem that we're trying to solve. So basically, we have this loss function, this in generic terms cross-entropy function that basically tries to match the probability distribution that our model is telling us the data has to the distribution that we are getting from nature in the data. This, remember, we saw last week, depends on the kind of problem that you have, the activation, how you interpret the network. So we have different loss functions, mean squared error for regression, logistic loss for binary classification, the softmax max loss for the multi-class classification, so on. But the idea is always the same. We have this loss function, and we're going to try to minimize it to get the maximum likelihood parameters for the model. The actual details of how this is done numerically, I'm not going to go into great depth here, but I'm going to talk a bit about the different optimizers that are commonly used, so that you have an idea of the tricks they use and how they work. So one that we saw so far is the stochastic gradient descent, SGD. Basically, the basic operation of this is to use the gradient vector and then multiply it by some small amount so that it takes a small step in that direction. There is one thing that you can also do here is to use momentum. Momentum we saw last week. We are using the gradient information at some point, at some time, to get a change in the velocity, and then we use that velocity to change the parameters. This means that if the gradient vectors are in the same direction over many iterations, our velocity starts to increase and we start moving faster in that direction. If the gradient vectors change too much, then the velocity will be small because they keep changing direction. So this is this class in Keras optimizer, or you can use that in TensorFlow. This is actually the same class, they are just pointing at in the different places. Undergrad is a bit more sophisticated. So one problem with the stochastic gradient descent is that we have the same step size, the same learning rate for different parameters. And sometimes different parts of the network or the input or something like that can have some may be going faster than others, or some may have higher gradients than others, and the velocity with which different parts of the network are learning can be different from one part to the other. And this may not be ideal. So undergrad keeps the sum of the squares of the gradient. So the square of the gradient gives you an idea of how large the gradient is, regardless of the direction, and keeps this sum for all parameters. And then it divides the learning rate by this value for each parameter. This means that those parameters that so far have been having larger gradients will now slow down learning, and those that have usually smaller gradients will have a higher learning rate. This means that parameters will tend to learn at the same rate, so have changes of the same magnitude during training, regardless of whether they have large or small gradients. But it also means, since undergrad keeps the sum of the previous gradient squared, or the sum of the magnitude of the previous gradient, the overall training rate is going to go down gradually over training. Because the sum keeps increasing, and since it's dividing the learning rate by that sum, it keeps slowing down. This is good for convex problems, which are those where the optimum value is somewhere in a valley, and you should go slower and slower as you approximate the optimum, so that you don't overshoot and don't go outside the best range. So this is another optimizer that you can use. You have here Adne, just use that instead of SGD, for example, and you can use this one. RMSProp is similar to Adne, but instead of keeping track of the sum of the squared gradients, it keeps the root of the mean of the squared gradient. So this RMS, it's a moving average, or it's not quite a moving average, it's the average of all the gradients so far. And this also has that effect that by dividing the learning rate by this RMS for all the parameters, parameters with smaller gradients will have a larger learning rate, and parameters with larger gradients will have a smaller learning rate. So this evens out the magnitude of the changes of the parameters in the network. However, since this is an average and not a sum, the learning rate, the overall learning rate, does not go down as training proceeds. So this is good for non-convex problems, which are those where we don't want to slow down. For example, for recurrent neural networks. We have neural networks where we feed the output of the network into the network itself, and we do that for time series. You're going to look at, well, I'm not sure. You're going to work on these kind of problems on the assignment, but I think you're going to use transformers and not recurrent neural networks. I'm not sure if Professor Rodrigues is going to use these two for comparison. But in these kinds of networks, we don't have this same kind of convex problem. So RMSProp is very used in recurrent networks, and in fact it's famous for being the most widely used optimizer that was never published, because this was presented in some workshops and then people started to use, and it ended up never being officially published despite being well known. A more recent optimizer that many times it's the default option because it's very efficient, it's Adne. It uses the same kind of approach of the previous ones of adjusting the learning rate for the different parameters by looking at the history of the gradients, but in this case this is an exponentially decreasing moving average. So it's going to consider what the gradients were in the previous iterations, but then it's going to start forgetting if we go too far along. So in a lot of epochs back, it does not matter what the gradients were, just the gradients as they were in the most recent epochs. And it also includes momentum, so it can be very fast. However, it is a bit too efficient, too greedy, and it has convergence problems. So sometimes it doesn't work very well, and you see many oscillations in training. But if that doesn't happen, it's really very efficient, and it makes the network learn very fast. So there is no real theoretic foundation for telling you which one to use, but I would say experiment with Adne. Adne is very fast. If you have problems, then try the others, Adne or SGD, or reduce the learning rate. But this is just to give you an idea of different approaches and the sophistication that these algorithms may have. It's not just a matter of looking at the gradients and applying that. It's actually you may do several different things to try to optimize training. So one thing that you need to look at when training the network is the training and validation plot. If you see these kind of things, a large oscillation on the training loss over different epochs, This means that you are using an optimizer that is taking the steps that are too large, so things are not stabilizing, and you are overshooting and making things worse sometimes. So if this happens, you should reduce the learning rate or try different optimizers so that you avoid these oscillations on the training loss. Note that oscillations on the validation loss may occur even when everything goes well, because the validation loss is not being measured on the same data set. So things may improve on the training set, and you may lose some performance on the validation set, but that can happen. However, the training loss should not oscillate, it should reduce gradually, and if this happens, then it's not a good sign. So basically, you can try to make your training, your learning rate as high as possible, so that it speeds up learning, but not so high that you get those kinds of instability. So check the plots. You can experiment, for example, with a subset of the training set. Yes.
It looks a bit weird to me because the scale is important to see those oscillations, right? Mm-hmm. So is there like a percentage mark?
No, it's, if you have a scale that goes around the values that you have, then, for example, if you plot including 0, it should not be a problem. Okay. Of course, if you don't include 0 and you always put the minimum and the maximum, then yes, you're always going to have oscillations. Although you should, even then, it should not be a problem, because if you're plotting over different epochs, it should steadily go down. Maybe once in a while go a bit up, but the trend, the descending trend, should be more important than the oscillations. Okay? So if you have something like this, where the oscillations are a lot larger than the trend, then it's very unstable.
Okay.
So this, you can experiment with a part of your training set, not the whole training set, so you can run more epochs quickly and have more data points here, and just to try to fine-tune these parameters. This can be one approach. Another important thing is the selection of the weights in the neural network. Remember, we saw last week that we cannot have the same weights for all the neurons in a layer, because that would give all the parameters, all those weights, the same gradients, and so they would all be trained in step, and the neurons will always be the same, equal to one another. So we need to break that symmetry, and so we randomize the initial weights in the network. But the problem is that if we have large values, when we are multiplying this by the input and summing everything and multiplying again, we can have huge values, or positive or negative, and then we can have problems with the overflow. So there are these initialization methods. We saw something very simple last week, which was just divided by the number of features that we had into the layer. But this is one example. The Lagoon normal initializer initializes the weights for each layer using a normal distribution, so centered on 0, and the standard deviation is the square root of 1 over the number of inputs into the layer. So this fan in is the size of the fan that is going into the layer. So basically, how many weights there are in that layer. So if a layer is receiving many different values, and that neuron has many weights, then the weights are initialized closer to 0. If it has fewer, they can have larger values. Of course, what this neuron will feed into also has importance, and this is the default initialization in Keras, the Gloro uniform initialization. Uses a uniform distribution, not a normal distribution, and the range is between these two values. This is the square root of 6 over the sum of the two fans, the input and the output. So for each neuron, you're looking at how many weights it has, how many inputs it's receiving, and also looking at how many neurons you have on the next layer. And the sum of this is what you divide there, and this gives you the range in which the weights are selected. So the idea here is basically to try to keep this close to zero, to break the symmetry by using random values, but scale this randomness so that we don't have values that are too large. And this depends on how many inputs there are into the neuron and how many neurons we have on the next layer in this case. So there are more initializers that you have in Keras, but just to give you an idea that you can choose this, yes?
Why are large values bad?
Because when you keep doing these products and sums, if you have large values, you can quickly overflow the numbers, right? And then you have problems with overflow. Another problem is if you have very different scales on the neurons, because you have a fixed representation, float 32 for example, and if you are doing a multiplication and a sum with very different scales, some of them will be out of the precision, and so they will not count. And that can cause problems then with the gradients and so on. So everything should be more or less on the same scale, so not to risk to have those not a number that sometimes appears, or wildly different scales that have then rounding errors when you are trying to train the network. Note that this is only for the weights, the values that you multiply. The bias values can generally start at zero. It doesn't matter if they're all zero, because the bias values for the neurons just adjust when the neuron is going to fire. They are not being multiplied by the digits.
Just a small question. If the values should not be too big, why not cut off them at a specific value?
At a fixed value? Because the range here is also important for making the neurons different, right? So this randomness,
yeah.
Suppose ultimately you put everything at zero, then nothing works, right? Because they're all the same, they all start at zero, and they will always keep the same, all of them equal. So you need some randomness to break the symmetry between the neurons so that they are different. And if you start with very, very, very small values, it takes longer to learn, because then the gradients are very small, and then everything takes a longer time. So basically, you should have this as high as possible before it starts giving you problems. And these are empirical attempts to do that. One important thing when we use neural networks that we saw is standardizing or normalizing the inputs into the network. But if you imagine that we can think of a network as a series of layers, and we can think of the network starting from any of these layers and receiving as input what the previous layers have produced as output. So the idea here is just like what we do to the inputs of the network, we standardize. We can standardize the inputs for the second layer, and the third layer, and the fourth layer by doing standardization on the outputs of the previous layer. And that's the idea here of batch normalization. So what we can do is we compute these running averages and standard deviations of the activations of layers during running. We keep moving averages of those values. And just like we do for the inputs, we are doing for all the layers on the network, or the layers that we want to apply this. So this is easy to do in Keras because you have a batch normalization layer that you can just put between the layers. And it makes learning faster, because by standardizing so despite this is being called batch normalization, it's actually standardization. But by standardizing the inputs into each layer, that layer is always seeing the input values centered at zero, and a cloud that is symmetrical and with a standard deviation of 1 on all the dimensions. Without this, the previous layer, as it changed during learning, could be shifting the data to one side or the other, and the next layer would have to relearn things according to those shifts. So if we standardize between layers, we can help the network learn because we are simplifying the task. So this can be done using batch normalization. You can add batch normalization layers, and basically they can use the batch for computing the standardization parameters, the mean, the standard deviation, and also keep a running average of those values, and then store that at the end, so that when you apply the network for prediction, you are using those fixed values that were learned during training. Okay, another problem, this is basically for optimizers for finding the best parameters for the networks, and now these are methods for improving the training itself, making it faster and go where we want it. But then there is the problem of optimizing the performance of the network, and for this, the major problem is overfitting, because with the deep neural networks we can have hugely complex models that are very powerful, and eventually they fit too well to the training data and start performing poorly outside the training set. So when we are using supervised learning, and even though we're going to see some examples of using neural networks for unsupervised learning, but that is in the sense, from our perspective, unsupervised in the sense that we don't need labels. But from the perspective of the network, it's always supervised. We are trying to adjust a target value. And basically, we always want this to generalize to outside the training set. So in these cases, the problem of overfitting is one we should be concerned about, because we can adjust too much to the training data and then lose the ability to generalize outside the training data. So there are two ways of trying to mitigate overfitting. We can select a model that does not overfit, that is not so powerful that we lose the generalization. However, this requires that the model be less flexible, less able to adjust to the data. And so we are losing on that side, and sometimes that is important. Another approach is use the same model, but adjust the way it is trained to try to mitigate overfitting. So this is basically model selection, selecting the best architecture, and regularization, adjusting the training to reduce overfitting. One thing that we need to do to combat overfitting is to measure overfitting. And for that, we need to compare the performance on the training set with the performance outside the training set. One method that we saw last semester, and that is widely used in machine learning in general, is cross-validation. We split the data into a number of folds. We train with all the folds except one that we leave outside for validation, and then we measure the error on that fold. So in this example, these points here, the small points, were used for training, and the larger ones, that fold there, was used to compute the loss, or the error in this case, after training. And then we leave another fold out, and we keep doing this with different folds left out, and we average everything in the end. This is good because it gives us an average estimate of how well this model performs on this kind of data. So when we train and obtain a specific instance, a hypothesis, and we do that over and over again, we get a better estimate of how well the model performs for these data. Yes?
So we also average the weights and everything?
No, this is just averaging the loss value, or the loss function, or whatever metrics we want. However, despite this being very used in machine learning, because we usually have algorithms that train very quickly and not much data, this is not generally used in deep learning, because if it takes a week to train the network, then doing 10-fold cross-validation would take 10 weeks, because you have to train again, and this is not very practical. Also, usually we don't use deep learning unless we have lots of data. So one advantage of cross-validation is that we don't need so much data to get a good estimate of these differences between training and validation error. But if we have lots of data, then we can just leave one part for validation and train on the rest. So usually, even though cross-validation is very used in classical machine learning, for deep learning the approach is just to use a validation set and a training set for this part. Usually we leave a test set out at the beginning so that we can have that unbiased estimate of the true error at the end, but for during training we use training and validation instead of cross-validation, because cross-validation tends to be too expensive to use in deep learning. So basically this is the approach. We use a training set to compute the best set of parameters by minimizing the loss function. The validation set allows us to check if there is problems in generalizing outside the training set, so that we can select the model, the regularization parameters, and so on. But if we are doing that, if we are using the validation set to optimize things, then the validation error will be biased, because we are fiddling with everything until the error is as small as we can get it. And so it will tend to underestimate the true error. If we want to have an idea of what the true error is, the true error would be the average error over all the possible examples we can meet in the future, then we need a test set. We need a set of data that was never used to optimize anything, that is just left so that at the end we can measure the error and have an unbiased estimate of the true error. So this is the general approach. It's what we saw last semester. Leave out a set of points for estimating the true error, if that is important. Usually on the exercises here we will not do that, because for the exercises that is not important, but on a real application you should have an unbiased estimate of the true error. And then with the data that you're going to use to optimize the network and try to get the best results, use a training set to compute the parameters and the validation set to compare the different architectures, regularization, and all of those things. So, model selection, we need to see if the model is adapting too much to the data, and in that case we can have a low training error but a relatively high validation error. So this is an example of solving the miles per gallon problem using this network with 150, 10, and 1 neurons on these layers. And we have a training error here. This is the mean square error. And we have the validation error here in green. So you can see that the validation error is significantly larger than the training error. This means that the network is learning things about the training data that do not generalize outside that data. So we need to simplify the model if we want to do model selection and improve things in that way. This is an example with a smaller network with 30, 10, 1 neurons. And now you can see that the validation error is smaller. And it's very close to the training error, but the important thing is that these graphs are in the same scale. The validation error drops from here about 7 or something to 3 around there. Okay? So we have an improvement in the ability to predict outside the training set. Of course, the training error increased a bit because this is a smaller network. It's not as able as the other one to adjust to the patterns in the training data. But the important thing is that the validation error is small. So this would be better than using the other one. If we have both of them very high, so if we compare these two, even though the training and validation error in this one is the same, so there is no overfitting in this network, this is not a good option because the overall error is higher. So this would be a better choice than the much simpler one. And here we can see a different problem, which is called underfitting. That happens when the model does not have enough power to actually learn the patterns of the data. So it's too simple for that kind of problem. And basically, model selection consists in trying to identify if you are overfitting or underfitting, and finding the model that minimizes the loss outside the training set. The reason why we plot the training error here is not that the training error itself is important, but it's the one that can indicate what problem we are facing when we compare it with the validation error. So our goal is to have a validation error that is as small as possible. But if we have a big difference between training and validation error, we are in overfitting and we need to simplify the model. If the validation error is high, but there is no difference between training and validation, then we are in underfitting and we need a better model, a more complex model for solving that problem. Okay? So remember, the point is not to minimize the difference between training and validation error. That is by itself not meaningful. The objective is to minimize the validation error, but comparing it with the training error lets us know if we are with a model that is too simple or too complex for the problem we're trying to solve. Okay, and this brings us into these concepts that we saw.
How can we know the size of the network without trying over and over again? Like, I have the size of the data set, right? How can I know that a 30, 10, 1 is better than a 100, 10, 1?
Before looking at the result, you cannot say that, because what makes the difference here is the kind of patterns that you have in the data. So suppose that you have data that is just one-dimensional. You only have one feature. But imagine that the classes are distributed like this. For example, class 0 is on one side and class X is on the other side. So this would need a very simple model to separate it. Or even simpler than that. But now imagine that you have like this. The points are all mixed together and you have alternating the class. So now you need something that is capable of creating all these separations, and this would require a very complex model. Okay? So the power of the model that you need, you cannot see just by looking at the dimensions of the data, something like that, because it depends on the patterns that you have. And that's why you usually have to experiment and try different ones, okay? Because it depends on what the actual shape of the classes are in your data. So these concepts of bias and variance, the bias is an average deviation between the predictions and the target value. So this means that if we have a model, we train it on different data sets, we obtain different hypotheses, and we look at the predictions of those different hypotheses for that model, we have a high bias when the average of the predictions for some particular point all have a distance to what we wanted to predict. So the bias is this difference between what, on average, instances of this model trained with data from this distribution will predict compared to what the actual value should be. So bias tends to be high when the model is stiffer and cannot accompany the data well, for example, like this, because it will have parts that cannot be close to what the actual points are. Variance is a measure of how scattered the predictions of different instances of the model will be when we train the model with different data sets. So if the model is very powerful and very sensitive to small changes in the training set, it can give wildly different hypotheses when we train it on different training sets, and thus can have a very large scattering, a very large dispersion of the different predictions in those different hypotheses for the same value. So the contribution of these two components to the error are basically that if we have a high bias, even though we may have a low variance for very simple models, we can have a large error because of the error committed by not being able to follow the data. On the other hand, if we have a very powerful model that can have a low bias, but if it's too sensitive to details in the training data, it can start making lots of errors outside the training set. So what we generally need to do is to find some spot here, if we are selecting different models, where we minimize the contribution of both bias and variance, and there is this trade-off. Usually more powerful model has lower bias but can have higher variance, and vice versa. Now, one thing that we can do with high variance and low bias that we cannot do with high bias and low variance is to adjust the training of the model to try to optimize performance. So if you have a model that has a high bias, for example, this type of thing here, there is nothing you can do to train this model that will improve its performance, because the model is simply unable to reach the correct positions on the space that we are working on to predict the data. But if we have a high variance, we can try to reduce the variance by constraining somehow the way the model is trained. So not allowing it to scatter so much and trying to limit its ability to spread all over the place. And this is what we can do with regularization. So regularization is any change in the training of the model that tries to minimize this problem of dispersion, of learning too much the details that don't generalize, and that results in high variance. So basically, we are trying to reduce variance by changing how the model is trained. One way of doing this is to try to restrict the range of values the model can learn. So we have all these parameters in the network. If the parameters can be whatever values they happen to be, the network can be can change very wildly from one training set to another. But if we force all the parameters to be small, then the network will be better behaved, will not change so much. And this is one way of reducing variance. So we can do this by adding to our loss function not only the original loss function, the one that gives us the maximum likelihood solution, but also add a term that is a function of the parameters of the network multiplied by some constant alpha to adjust how much that weighs. And this function usually takes one of these two forms. In L2 regularization, this is also called ridge regression for regression problems, we have this penalty that is the square of the size of the vector. So we imagine that this vector has all the weights of the network, and now we measure the square of the magnitude of that vector, and that would be the parameter, the penalization that we add to the loss function. Also, we can alternatively use L1 regularization. This is also often used, which does not is not the square of the size of the vector, but the sum of the absolute values of all the individual weights. There is a difference here. I'm going to talk a bit about that, but just to note that this is generally applied to the weights of the neurons, so that those parameters that multiply the input, and not to the bias value. The bias value is usually left free to adjust, because that is just to adjust where the neuron will fire. If we use L2 regularization, this is also called weight decay, because when you take the derivative of that function, the update rule for the weight becomes the previous weight minus a fraction of the previous weight. So this epsilon is the learning rate, the alpha is how much regularization we want, so this weight here, and W would be the previous weight. So we are, for each parameter, when we update that parameter, we take a small fraction of what the parameter was. So we are decreasing the size of the parameter in proportion to what the size was, and then also whatever contribution the original loss function has. So basically, if a parameter, if a weight of a neuron is not contributing much to reducing the loss function, it will tend to gradually shrink in magnitude over the iterations, and this is what is called, why this is also called weight decay. So it's decreasing gradually. But note that it's always decreasing in proportion to the value that it had. So it's not going to jump to zero, it's going to shrink slower and slower as it's smaller and smaller. So basically, L2 regularization makes the overall vector of parameters as small as possible, but it's penalizing more parameters that are very large and penalizing less parameters that are smaller. With L1 regularization, what you have in the derivative here of the loss function, including the regularization term, is a term that is just proportional to the size, to the sign of the vector. So if it's of the parameter, if it's positive, it will be positive. If it's negative, it will be negative. So basically, when we update the parameters, we are chopping off a constant value of and not something that is proportional to the size of the parameter, and this will tend to shrink the weights to zero. So with L1 regularization, those parameters that are not very useful to minimize the original loss function will tend to be set at zero, and only the ones that are useful will be different from zero. So basically, L2 regularization will penalize more the largest values and try to shrink everything as much as possible, although it will not worry so much about parameters that are small, so they will not be shrunk further. L1 regularization tries to minimize the number of parameters that are not zero. So it's going to, everything that is not necessary will be switched off. Another way of doing regularization is to increase the size of data. So the larger the training set we have, the fewer problems we'll have generalizing outside the training set. If we have a problem where we can synthetically create new examples, then we can apply this method, data augmentation. For example, suppose we have an image classification problem where we're trying to find faces. We can do things like inverting on one axis or rotating the faces. If we are trying to find faces in any different orientation from the original source image, we can create different images with different orientations. We can also apply distortions to the face, so it's still a face if the nose is a bit crooked or one eye is not exactly the same as the other or something like that. So we can apply these transformations to the data and still have valid data, but we now effectively, from the perspective of the network, have a larger training set. So this can help reduce overfitting by improving generalization. Of course, you need to use only transformations that are appropriate for the problem. For example, if we have a face here looking to the right, we can flip that and put it looking to the left, and this would still be a face. But if you are doing, for example, character recognition, you cannot flip a P because then it looks like a Q and it's no longer the same letter. So you cannot do that arbitrarily on all problems. You need to find for each problem what transformations you can do without making the data wrong. So one general approach here, if we don't have these kinds of transformations that we know are safe, is to do data augmentation by noise injection. So imagine that before inputting an example into the network, we add a random noise, for example, normally distributed noise, but with a very small amount. So we are making very small perturbations to the vector, so small that we know they won't change the example. It will not stop being the original class and not stop being a reasonable example. But these perturbations are sufficient to make the network more robust and not as specialized into the training set as we have. We can also apply noise to the weights of the network or even to the output. For example, suppose that we have a binary classification problem and we have a sigmoid output. If we say that examples in class 0 must have a 0 probability of being in class 1, and examples of class 1 must have a probability of 1 of being class 1, so that would be what the sigmoid output is telling us. We are forcing the weights to be very large because the sigmoid only approaches 0 at minus infinity and 1 at plus infinity. We can create a bit of smoothing on the labels by using a small value, so that, for example, for class 0, the target value for the network would be 0.01, and for class 1 would be 0.99, and so now we are not forcing the network so much. This can even be used to model uncertainty in the labels, because sometimes the data set that we have is not all 100% correct. There may be some things wrong there, so we can include that in smoothing or adding noise to the labels and so on. Another very used method for regularization in neural networks is early stopping. This is an exaggerated example with lots of overfitting, but it's just to make things easy to see. You can see, even though the training error keeps reducing, the validation error goes low here and then starts increasing again. So this means that as we are training the network, the weights are being adjusted to the training set, and eventually they start to become over-adjusted to the training set, and we start losing performance outside the training set. So ideally here, we should stop training somewhere here around 12,000 epochs or something like that, and not continue further on, and this would give us the best instance of the model. So this is something that is usually done. You store checkpoints at regular intervals, for example, and then when you see that you start overfitting, you go back and pick the best one, or you keep track of validation error, and if it no longer is reducing, you stop training. So you can do that easily also in cache and stop training automatically. This is very useful in training neural networks, not only because it reduces overfitting, but also it's computationally very cheap. We just stop training, and that is better than adding additional computations. Another thing that we saw last semester that we can do to reduce overfitting is reducing variance by averaging the results of different instances of the model. We did this with bagging, where we used bootstrapping to generate replicas of the training set. We trained the same model in different instances using those replicas, and then for prediction, we run through all the instances and we average the predictions. So even though the model may tend to give us wildly different hypotheses, given different small differences in the training set, when we average those hypotheses, the variance is lower. The variance of the average will now be lower. So this is done usually in classical machine learning by obtaining many instances of the same model. Of course, with deep neural networks, that would not be very practical because each one has a huge memory footprint and takes a long time to train and so on. However, there is one way of doing this implicitly, which is using dropouts. Dropouts randomly turns off a subset of neurons on a layer, and you can apply dropouts all through the network. So when you present a batch of examples to the network, some of the neurons will be switched off and will be ignored, and only other neurons will be used. And when you present a new batch, the dice will be rolled again, and another set of neurons will be chosen. So for each batch, you are training a different network that results from different combinations of the neurons in the layers. And this effectively is training a family of neural networks implicitly using only one neural network, because things keep changing from batch to batch, and this forces the network to learn in a way that is not sensitive to whether or not some neurons are active. So basically, dropout, which is this approach by turning off, by dropping out at random some neurons, will give us the result similar to an ensemble of networks, but by training only on a single network. And this is a very efficient way of reducing overfitting with deep neural networks by adding these dropouts to the different layers. So one thing that we need to do is to rescale the weights of the neurons between training and then when we are doing inference, when we are predicting with the network. The reason for that is that after training we will no longer be dropping out neurons, we're going to use the whole network, but now neurons that on average were turned off, for example, 50% of the time, now are always active. And so this may require an adjustment to the weights of the next layer that are going to be receiving these neurons. So one way of doing this in dropout is that after training, the weights are rescaled based on the probability of the neurons that are giving them inputs were ahead of being turned on. In inverted dropout, these, instead of the weights being adjusted after training, they are increased, the activation values of the neurons that are dropping out is increased in proportion, so that things even out at the end. Okay, but in any case, when you're using these in tethers, this is done automatically, but you just need to remember that the scales during training will have to be changed relative to the scales after training to compensate for the fact that after training we are no longer dropping out neurons, but we are using the whole network. Another feature in neural networks is that given the power and complexity of the model, it can really fine-tune and adjust the discriminants, the places where it separates the different classes. And this can be a problem. Again, contributes for overfitting. This is an example of a network trained to classify images, and if we present this image, the network tells us it's a panda. This is the class with the largest probability and with a probability of 57%. But now suppose that you take the gradients of the pixel values here, of the loss function with respect to the pixel values for this particular case. So we look at how important each pixel is, or how sensitive the classification is to each pixel by looking at the sign of the gradient here. So some pixels going up or others going down would lead the network to try to change a lot the loss function. So if we take this image here created by looking at the gradient of the loss function with respect to the pixels and add it to the original one but with just a very small fraction so that the result looks to be the same, but it's still enough for the network to change class. So in this case, it now classifies this as a gibbon with 99% probability. Because we transformed the initial image in the direction that has the greatest impact in the loss function. So it's also in the direction where things will change much for the network. And that's enough for the network now to be misled. The reason why this is happening is because the network learned to make some separations between the classes, but never met these kinds of examples that were almost the same as one example of a class, but modified in a way that maximizes the impact on the loss function. And so this is an example of overfitting because now the network is too fine-tuned for those particular frontiers. One way of solving this with adversarial training is to actually add these transformed images to the training set. So we know that if the gradient of the loss function is too high with respect to the input values for some particular examples, this means that the classifier is very sensitive to variations in those input values. So now we add changes to those input values, we add that to the training set, and we try to make the classifier less sensitive to this. So adversarial training does this automatically by looking at the transformations that have the greatest impact and add those to training. Of course, this has a problem in that it's computationally demanding, because we need to compute the derivative of the loss function with respect to all the pixels in the input, and this takes time. So one way of doing something similar to this would be by noise injection. Noise injection is much simpler. This is what we saw here with the phases. So we can do dataset augmentation by noise injection. Instead of computing which changes would have the largest impact on the network, we can just put random changes, and it also helps make the network more robust. But this is also an important problem nowadays if you use things like automated driving and so on that need to understand, for example, traffic signs. There was one example recently where a zone with a 35 miles per hour speed limit, someone glued a very small piece of black tape on the middle of the street, and the automatic cars, I think were Tesla cars, started to accelerate to 85 miles per hour because that very small change, and the car thought it was an 8 and not a 3. So a human looks at that and still sees a 3 because it's just 1 or 2 centimeters on the middle of the 3, but for the image recognition part on the car, it made all the difference, and the car started to accelerate. So these things, there are dangers here, and these kind of approaches of figuring out what the classifier is sensitive to help try to minimize those problems. So basically, there are lots of things you need to select, different models. We have searching potential possible architectures is very hard because it's a very large search space. Different regularization methods, different weights for that, and so on. And basically, what you generally have to do is some experimentation. Look at the results with a small subset of your data, optimize things like learning rates, the optimizers, and such, and then check for overfitting and try to minimize that. One thing that you need to remember is that if your model is overfitting, you can try to apply regularization to reduce the generalization error. But if the model is underfitting, there is nothing you can do because the model is not good enough to solve the problem. So generally, we try to create the network so that the loss on the training set is small enough, even if it's overfitting. And then we do things like regularization to try to minimize that problem. But if your model is too simple, then you cannot improve things if it's underfitting. And this is often a problem because you need a model that is sufficiently complex to capture the right patterns in the data that you have, but you may not have enough data to prevent that model from overfitting. So usually you need to use regularization in deep neural networks to try to improve results. So to sum up, we saw different aspects of this optimization problem: the optimizers to look for the parameters, to optimize the actual training of the network to try to make training faster, and then optimizing the predictions of the network, selecting the right models and using regularization to reduce overfitting. So these chapters here in the book, you can take a look, cover different aspects of these problems.